Hi, today I'm going to introduce how to solve problem D, Divisor card game. Um, in this problem, you have to simulate a card game. So there are n players, and there are n cards, where each card is labeled with a positive integer. So before the game starts, each player will receive an non-empty subset of cards, and at least one card is undealt. So suppose there are K cards that are undealt, and the game will proceed in K rounds. In each round, an undealt card C is chosen uniformly at random. Then the card is given to the player whose hand contains the smallest multiple of C. And if no such multiple exists, the card is then discarded, and it will not be used in subsequent rounds. And each player, in this problem, we assume each player will always place the smallest possible multiple of C, which is a quite easy strategy to come up with. And or if there's no card that is the smallest multiple, then they will just play the smallest card. And the problem is to determine the expected number of cards each player will receive by the end of the game. First, we can make some easy observations. Because these observations are I think they're quite easy. So I will present the proof here. So the first observation is that for any card C, if C is not owned before any round, and there are no other multiples of C exists, uh, or no other multiple of C is handed to anyone, then C must not be owned by the end of the game, or otherwise this card will always be owned by someone. So this is a quite important observation in this problem. So we'll use this observation multiple times in our solution. So what we can do here is we simply discard the cards before any round. That is, if we found the card C that satisfies this criteria, we just remove them. And the second one is that we can model the game as selecting a random permutation of the undealt card. So the original game is to randomly select a card in each round. And now we just model the game as selecting a random permutation. So the key idea of this solution is to define a thing called the winning sequence. So if we look at the game, so it is quite obvious that if we want a player I to obtain a card J, then it always follows a chain of plays, uh, like Z0, C1, C2, C3, up to CK. And in this sequence, each subsequent card is won by playing the previous card. So for example, C4, if we want to obtain C4, then you have to play C3. And C0 is initially owned by player I. So the solution here is to summing up the probability over all possible winning sequences that start with a card owned by I and ends with a card J. By adding all the probability of this winning sequence appears in a random permutation, we get the probability that the player I wins card J. And then we just try to sum up all J for each I, then we get the answer for player I. So this is from the linearity of expectation. So the solution here, the problem here is to fix a winning sequence, and we try to calculate the probability that this sequence occurs. And this turns out it has a pretty clean formula for this problem. So let PT be the number of undealt cards before any rounds in this range, and that are divisible by CT, and they are not discarded. The discarded, not discarded means that this criteria, okay, this criteria. It turns out that the probability that this sequence happens can be calculated as this formula, which is the product of all surface sums, as you can see here. So this formulation actually suggested a pretty simple dynamic programming solution. So because enumerating all winning sequences is too slow, because there could be a lot of them, so we have to use dynamic programming to speed up our solution. And let DPIS, this formulation, be the sum of probability mass of winning sequences. So this winning sequence ends at the card I. It actually starts at card I, which is the because we do in reverse order. So in fact, we first encounter CK, then CK plus 1, CK minus 1, up to C0. So the winning sequence that starts at CI, where the cumulative sum of PT, which we describe as the suffix sum here, is S. Then from this formulation, we can just do a pretty standard dynamic programming part, and because this is the product of all suffix sums, so we just try to find for each I, for each I we found a J, that I divides J, and J is not discarded, and let P be the number of undealt and not discarded card. This is the same as the PT we mentioned before. So then we just try to assign this formulation. So to calculate the answer for player I, we just simply sum over DPCS, where C is a card the player I initially owns, and we just try to sum up over all S. So this solution runs in O(n) cube time, and there's one pitfall contestant may make is to remember not to count the sequences that there is at least one dealt cards between consecutive winning sequences. Because if there's at least one dealt card between CT and CT minus 1, and from the observation before, the winning sequence will not go like this, and will play the dealt card before instead. So from the observation, the probability of such sequence occurs is 0. So the author solution is around 1600 bytes, which is not very long. And another thing that worth mentioning is that this problem might tempt contestants to try some very easy DP approaches. For example, some contestants may found that let DPIJ be the probability that the I player wins the J's card, or something like that. But most of them turn out to be incorrect. And these solutions, mostly they're incorrect, mostly because they usually falsely assume that independence holds between some events. And this is the common mistake that many people make when they try to solve this problem. And and this is how I introduce how to solve the problem. Thank you.